To the next heading, beta. Change in state. Change in state. Change in state is nothing but beta, the process of converting a substance from one state to the another state without change of your temperature. It is called as of your change in state. Okay. It is the process of converting a substance from one state to other state. From one state to your other state without change of temperature. Without change of temperature. Am I clear? The process of converting a substance from one state to your another state without change of your temperature is called as of your change of state. Like say for example, I'm having a solid, isn't it? I'm converting solid by a process called as melting to a liquid. Okay, liquid, you know that on boiling can be converted into your gas. Okay, the same way, gas can be converted back into liquid by a process called as of your condensation. Okay, liquid by a process called as of your freezing. We can convert back into your solid. Am I clear? And we are having one more process, beta. Converting the solid directly to your gas by a process called as of your hot burst. Okay. In the same way, converting a solid or gas to a solid by a process called as of your sublimation. Clear? Chalo. Next one is latent heat. Latent heat. In Greek, latent means hidden beta. The energy which is present in the body is called as of your what? Latent heat part. Like say, it is the amount of heat required to convert 1 gram of substance, 1 gram of your substance from one state to other state. Okay, at constant temperature. At constant temperature is called as what? Latent heat. Am I clear? What do you mean by latent heat, beta? So the amount of heat required to convert 1 gram of your substance from one state to your another state at your constant temperature is called as of your latent heat. Am I clear? So write the formula. Q is equals to your M into your L. That means latent heat L is equals to amount of heat given per your unit mass. So L is equals to Q divided by your M. Q is measured in energy, na? Joule. Mass is measured in kg. So unit is joule per kg in SI system. Isn't it? Or we can even say calorie per your gram in your CGS system. Okay. And you know that 1 calorie per gram is equals to how much, beta? 1 calorie per your gram is equals to 4,200 joule per your kg. 1 calorie per gram is equals to 4,200 joule per your kg. Okay, so latent heat of your body is given by the formula L is equals to Q divided by M. Amount of heat required to convert 1 gram of a substance from one state to another state at a constant temperature is called as of your latent heat. So Q is equals to your M into your L. So Q is directly proportional to mass. Removing the proportional to constant, we are getting L. L is known as right now for me latent heat. Unit is joule per kg in your SI system or calorie per gram in your CGS system. And you know that 1 calorie per 1 gram is equals to 4,200 joule per your kg. Am I clear? Chalo. Please try to remember these points by hearted better. Like latent heat of ice is always 80 calorie per your gram. That is equals to 80 into 4,200 joule per your kg. Okay. In the same way, latent heat of your steam is equals to 540 calorie per your gram. That is equals to 540 into your 4,200 joule per your kg because 1 calorie is 4,200. Okay. So when to use this value beta? Whenever there is an heat observed or evolved during the change of state, we directly use the formula Q is equals to M into your L. Okay. Here, heat observed, heat observed or evolved, heat observed or evolved during change of state, during change of state is Q is equals to M into your L. Am I clear? Latent heat of ice is how much? 80 calorie per gram. And latent heat of steam is how much for me? 540 calorie per your gram. You know that latent heat is equals to Q by M. SI unit is joule per kg and CGS unit is calorie per your gram per deflation. And 1 calorie is equals to 4,200 joule per your kg. Clear? Sure. Next heading. Journey of your ice. Journey of your ice. Let's say I'm having the ice at minus 20 degrees Celsius. Okay. So we are having ice at minus 20 degrees Celsius. Ice at 20 degrees Celsius, minus 20 degrees Celsius will convert into, tell me, it will convert into ice at your 0 degrees Celsius. Isn't it? So there is no change in state beta. Both of them are solid, but there is a temperature difference. Initial temperature is minus 20 and final temperature is 0 degrees Celsius. So here you can calculate the heat by using the formula Q is equals to M into specific heat of your ice into temperature difference. Okay. Then ice at 0 degrees Celsius will convert into water at 0 degrees Celsius. Water at your 0 degrees Celsius. So there is change in state. Ice is converting into water. Solid is converting into your liquid. But temperature difference is same. When temperature difference is same, but there is a change in state, then we'll be using the formula Q is equals to M into L of your ice. Done? Then water at 0 degrees Celsius will convert into water at your 100 degrees Celsius. Will convert into water at 100 degrees Celsius. There is no change in state beta. Water and water, both of them are liquid, but there is a temperature difference. When there is a temperature difference, use the formula Q is equals to Ms into your delta theta. Here it is the specific heat of water. Am I clear? This value you can use here as Q into mass of water, specific heat of water into temperature difference. Now water at 100 degrees Celsius will convert into steam at your 100 degrees Celsius. So when you're converting the steam at your 100 degrees Celsius, there is a change in state. Water is converting into vapor. Then in that case, you can write Q4 is equals to M into latent heat of your vapor or boiling point. Clear? Again, steam at your 100 degrees Celsius can be converted into steam at temperature greater than 100. So steam at your like 120 degrees Celsius. So change in state is not possible, but both of them are in same state, but temperature is difference. So at that time I can use Q5 is equals to M into specific heat of your steam, say for example of your vapor into temperature difference. So that will give me the value. So total amount of heat liberated means you can use the formula Q is equals to Q1 plus of your Q2 plus Q3 plus Q4 plus of your Q5. Am I clear? Am I clear?
Yes, sir.
So in the change in state, our journey of your ice when you're talking about ice at minus 20 degrees Celsius is first converting into your, it is first converting into your ice at your 0 degrees Celsius. From ice to ice, no change in state. No change in state. So when there is no change in state, use the formula Q is equals to ms into delta T. Then from ice to water, there is a change in state. Change in state. Solid is converting into liquid. Then use the formula Q is equals to M into L. Then from water to water again, there is no change in state. No change in your state. So when there is no change in state, use the formula Q3 is equals to Ms into delta T. Here S is the specific heat of water. Then again from water to steam, there is your change in state. Change in state. When there is a change in state, use the formula Q is equals to M into latent heat of your vapor. Then again, steam to your steam at 120 degrees Celsius. There is no change. There is no change in your state. So when there is no change in state, you will be using the formula Ms into your delta T. Am I clear? Any doubt in this one? Sure. Take an example better. Find amount of heat required. Amount of heat required to convert 10 gram of ice 10 gram of ice into steam at 100 degrees Celsius. Initially, ice is at minus 20 degrees Celsius. So try to do it. Okay. We are having first ice at minus 20 degrees Celsius. This will convert into your again ice at your 0 degrees Celsius. Ice will convert into your water at 0 degrees Celsius. Water will convert into water at 100 degrees Celsius. Water will convert into your steam at your 100 degrees Celsius. Okay. So here there is your change of your state. There is no change of state, ice to ice. So this will be equal to how much beta first one? Q is equals to ms into delta T. Here it is Q1, here it is Q2, this is Q3, and this one is your Q4. Okay, so Q is equals to your first one is right now for me or Mass. How much amount of the mass is given beta? 10. So it is 10 into specific heat of ice is half into temperature difference will be equal to how much beta? 20 degrees Celsius plus 10 into latent heat of ice is 80 plus again this is your 10 into specific heat of water is 1 into temperature difference is right now for me 100. Okay. Into your 100 degrees Celsius plus the next one is right now Q4. Q4 is right now for me how much amount of mass? 10 into specific heat of your, sorry, so latent heat of your steam, 540, isn't it? So this is two ones, this is your two tens. Anything else? Nothing, na? So it will be 10 into 10. This will be equal to your. Shall try to simplify and tell me what is the answer? Anyone? First, this is 100. This will be 800. This will be your 1000. This will be 5400. So
7,300.
7300 calories. Clear? If I need the answer in terms of joule, then what is the answer? Q is equals to 7300 into 1 calorie is equals to 4.2 joules. Okay. 4.2 means 42 divided by 10. So it is 730 into 42. How much it is? 3660 joules. This will be the answer. Am I clear? Try to do this one better. Calculate the amount of heat in calories in calorie required to convert 5 gram of ice at 0 degrees Celsius to steam at 100 degrees Celsius. Chalo, try to do it out.
3,600.
What is the answer, beta? Anyone?
3,600 calorie.
3,600 calorie. Very good. Need not do now.
Yes, sir.
5 gram of your ice at what temperature? 0 degree Celsius will convert into 5 grams of what? Water at 0 degrees Celsius. 5 grams of water at 0 degrees Celsius will convert into 5 grams of water at 100 degrees Celsius. And this will convert again into 5 grams of your steam at your 100 degrees Celsius. So it is Q1, here it is Q2, and here it is Q3. So total amount of heat is, first one is M into latent heat of your fusion of ice plus M into specific heat of water into temperature difference plus M into latent heat of your vaporization. How much amount of mass it is, beta? 5 into this one is 80 plus mass is 5, specific heat of water is 1, temperature difference is right now for this one 100 plus 5 into 540. So how much you are getting this one, beta? How much I told you? 3,600 calories. Okay, sure. The next one. Principle of calorimeter. Principle of calorimetry. So what is the principle of calorimetry, beta? Whenever two substances at different temperatures have been mixed, then at steady state, both will be attaining one common temperature, isn't it? When two substances, when two substances at different temperatures, different temperatures are mixed, okay, are mixed, then at steady state, both will attain a common temperature. Okay, so then we can say that energy released by one substance, energy released by one substance, energy released by one substance is equals to energy absorbed by other substance. Okay, so energy released by one substance is equals to your energy absorbed by the other substance. That is your principle of your calorimeter. What is the other way I can even say, beta? Heat lost by one body will be equal to heat gained by your other method. Principle of calorimetry is also known as of your principle of method of your mixtures, beta. Okay, heat lost by your one body will be equal to your heat gained by the another body. Okay, you can write this one as here. Heat lost by hot body is also equal to your heat gained by cold body. We can even roughly write like this. Okay, heat lost by your hot body will be equal to your heat gained by your cold body. Done.
Yes,
Sure.
sir.
See this example better. Let's say I'm having 80 grams of your water at your 30 degrees Celsius, isn't it? Are poured on a large block of ice, on a large block of your ice. At what temperature? At 0 degrees Celsius. Okay. So the mass of ice that melts is, the mass of ice that melts is, see, 80 gram of ice at 30 degrees Celsius is being poured into larger block of ice at 0 degrees Celsius. That means I can say that heat lost by water at 30 degrees Celsius will be equal to heat gained by ice. So what will be the final temperature is asking. That means when water at 30 degrees is being poured, it is still on the large block of ice. So ice will be at 0 degrees Celsius only, isn't it? So I can say that heat given by water must be equal to observed heat observed by ice. Okay, so it is mass of water, specific heat of water into temperature difference will be equal to ice at 0 degrees Celsius. It is m into L of your ice. Mass of water is 80, specific heat of water is 1. Temperature difference is, it is 32 going to ice. Ice will be at 0 degrees Celsius. Mass of ice, how much it is melted, I don't know. So it is m into latent heat of ice is right now for me equal to your 80. This 80 will get cancelled. So m will be equal to your, how much for me? 30 grams. Am I clear? Am I clear, beta?
Yes, sir.
Sure. Take one case, beta. See, if I say we have got two liquids, if two liquids of masses m1 and m2 of your specific heats or specific heat s1 and s2 and at temperatures T1 and T2 are mixed. Okay, then resultant temperature should be, then resultant temperature should be, okay, I'm taking in the bracket T1 is lesser than T and T is lesser than of your T2. T is your common temperature. So what is the principle I can say here? Heat lost by hot body, heat lost by hot body must be equal to heat gained by cold body. Heat gained by your cold body. Okay. So he is losing the heat beta. M1 and M2 are there right now for me. And T1 and T2 have been mixed. T1 is lesser than T and T is lesser than T2. That means T2 is greater here. So it is your M2 S2 into your, this is the T2 and it is attaining some common temperature T. And it is equals to heat gained by cold water. That is M1, this is S1 into temperature will be, this is T minus of T1. Because it is gaining, na? If initial temperature of the cold body is T1, after hot body has been mixed, it will rise from T1 to some common temperature T. That value we need to get. So just simplify this one. M2S2 T2 minus M2 S2 T is equals to your M1 S1 into T minus M1 S1 into your T1. Clear? So all the common temperature terms you take on one side. So it is your M2 S2 T2 plus of your M1 S1 T1 will be equal to your M1 S1 T plus of your M2 S2 into your T, isn't it? In this one, T is common beta. So I can write here M2 S2 T2 plus of your M1 S1 and T1 will be equal to your M1 S1 plus of your M2 S2 and this is at your common temperature T. So that common temperature formula is right now for me T is equals to your M1 S1 T1 plus of your M2 S2 T2 divided by your, this is your M1 S1 plus of your M2 into S2. So this is your common temperature formula for two liquids when they are being mixed. Okay. Now for n liquids, if I'm talking about, for your n liquids, when you're talking about, T will be equal to your summation of your Ms into T divided by your summation of your M into S. Okay. For n liquids, if I'm talking about, isn't it? Condition is like, say, example, M1 for the first liquid, specific liquid is S1 and temperature is T1. There is another liquid M2, specific heat is S2 and temperature is T2. Third liquid M3, specific heat is S3 and temperature is right now T3. So what is the common temperature means? I can directly use the formula T is equals to M1 S1 T1 plus of your M2 S2 T2 plus of your M3 S3 T3 divided by total specific heats M1 S1 plus of your M2 S2 plus of your M3 S3. Am I clear? Am I clear? Any doubt in this one?
No, sir.
Sure. I hope you are clear with this one, everyone. Sure. Take one question, beta, based on this one. If number of liquids of masses like M, 2M, 3M, so on up to Nm, and specific heats S, comma 2S, comma 3S, so on up to N, and at the temperatures T1, comma 2T, comma 3T, comma so on up to NT are mixed in a calorimeter. In a calorimeter. Okay. Of your negligible heat capacity. Okay. Then find the resultant temperature of mixture. Then find resultant temperature of mixture. Chalo, try to do it. We got how many number of liquids beta here? N number of your liquids of mass M, 2M, 3M, so on. So T will be equal to, I'm using the summation of formula beta. First one is Ms into T. Next one is right now for me 2M into 2S into your 2T plus of your, this is 3M into your 3S into your 3T plus so on up to N divided by your, this value will be equal to M into S plus this is 2M into your 2S plus of your 3M into your 3S plus so on up to your N. So in the above first part of relation, I can say that M into S into T, if it is common, it will be equal to 1 cube plus of your 2 cube plus of your 3 cube plus so on up to infinity divided by, then now it is again ms common, it will be 1 square plus 2 square plus 3 square plus so on up to infinity. Ms and ms will get cancelled here right now for me, isn't it? So there is a t still in the given condition, isn't it? So now tell me what is the formula for your 1 cube, 2 cube, 3 cube up to your infinity. I hope you remember this formula. So this is your T. In basic mathematics, we are having the formula for this one. It is n square into your n plus 1 into your whole square divided by sum of your natural square numbers 1 square plus 2 square plus 3 square plus up to infinity. It is given by the formula 4 into your, this will be equal to your n into your n plus 1. This is your n into your n plus 1 into 2n plus 1 divided by your 6. This is 2 2s are, this is 2 3s are. Again, this is n square. So this square will get cancelled. This n plus 1 will get cancelled. So common temperature will be coming out for me. The resultant temperature will be coming out for me. This is your T dash Alt. So it is your M into S into delta T. Everything is getting cancelled. So 3 will go up. So this will be equal to, again, this N and this square will also will get cancelled. So it is a 3 into your N into your N plus 1 divided by, this will be equal to your 2 into your 2n plus 1. This will be the answer. 2n plus 1. Okay. So this is the resultant temperature. Am I clear? Clear, beta? One last topic, beta. Then in tomorrow section, we'll try to go for your problem solving session on your calorimeter and as well as of your thermometer. Then we'll start with your thermal expansion of solids, liquids, and as well as of your gases, followed by thermodynamics. Okay. Next one is last topic of this one. It is your Joule's law. Joule's law says that work done is directly proportional to heat produced. Like say during winter we rub our hands to get the heat. Okay, and it is irreversible process. Okay, so work done when we rub our two hands, heat will be produced. So work done is directly proportional to your heat produced. So I can write here W is directly proportional to Q. Remove the proportionality constant, we get some constant known as of your J. So W is equals to J into Q, isn't it? J is your Joule's constant, or it is also called as of your mechanical equivalent of your constant. This is known as of your Joule's constant, or it is also known as of your mechanical equivalent of your heat. Okay, and J value is better 4.2 joule per your calorie. Okay, when work is in joules and Q is in calories. When W is in joules and Q in calories. Okay, and the same way J is equals to 4200 joule per your calorie. Okay, again when W is in joules and Q is in kilocalories. Okay, and J value is equals to 1 when both Q and your W are in joules. Are in joules. It means both of them are in the SI units. In that case, J value will be taken as of your 1. Okay, so therefore I can say that Joule's law in SI unit, SI unit, W will be equal to your Q. Okay, because J value I'm taking it as equals to your 1. Okay, work done can be anything better right now here. I can take this work done as in the form of potential energy mg into h, in the form of your kinetic energy half into m into v square, or I can take in terms of your kinetic energy, potential energy, any other given forms, whatever he gives, we can take that one into the consideration and try to do the numericals part of it. Am I clear?
Yes, sir.
Sure. Small example, we'll try to do it out. Then I'll send today one assignment based on this one. Then we'll try to discuss that one in the tomorrow session of your class. And also we have one important area of problems to be done when the mixture of your ice steam, when we have the mixture problems, how to do the mixture problems. In the tomorrow session of your class, we'll try to complete with the mixture problems of your calorimeter. Okay. Sure. See this question better. A body drop a body drop from a height of from a height of from a height of 10 meters onto a floor. Okay, it rebounds to a height it rebounds to a height 5.8 meter. Okay, if no heat lost to the surrounding, okay, and the floor, then find rise in temperature of the body. Rise in temperature of the body. Okay, so what is the condition here? A body is being dropped from a height. So somewhere from here, this is a ground. This is your 10 meter size. From here, this body is being dropped onto the floor. It will reach the ground and rebounds and goes up to your another height. If this is your H1, this is going to a height of your 5.8 meter. And there is no heat lost, is telling to the surrounding. Then find the rise in temperature. So here W will be equal to Q. And specific heat of the body is equals to specific heat of the body, that is given as 0.1 calorie per your gram degree Celsius. Clear? Chalo. So it is mg into your height of this body is h1 plus this is your mg into height is right now for me minus of h2, isn't it? Because it is rebounding. That will be equal to ms into your delta theta. Okay, so this value will be equal to, in this one mg will become common into this is h1 minus of your h2 is equals to ms into delta theta. M and m will get cancelled right now for me here. Specific heat of water is also given for me. Specific heat of body is given for me 0.1 into this is 4200 into temperature difference is delta theta. And G value I'm taking it as of your 10 and height is right now 10 minus of your 5.8. Okay. So this will be equal to your 10 into your, this is 4.2 is equals to, this is your 420 into your delta theta. Okay. Am I clear? So delta theta will be equal to your how much for me? So it is 4.2 delta theta will be equal to 0.1 degree Celsius. This will be the rise in temperature. Am I clear? Why to here minus beta? Because downward direction, if I am taking positive, upward direction, you take it as of your negative. Okay, difference of your height. Done?
Yes, sir.
Tomorrow session of your class, we'll try to do all the applications related to the calorimetry beta. When work done is in terms of kinetic energy and heat vagera. And tomorrow we'll also try to do the last topic of calorimeter, that is about your mixture problems. When water and ice and steam are mixed, how much amount of ice is being melted or how much amount of steam is being there, or what is the composition of your water, steam and ice in the mixture. That all type of problems we'll try to do it in the tomorrow session of your class. Okay? चल कुछ डाउट्स है आप लोग का, कुछ रिक्वायरमेंट है तो यू लेट मी नो बेटा. इफ देयर इज एनी रिक्वायरमेंट ऑफ ए टॉपिक दैट आई नीड टू डू इम्पोर्टेंटली फॉर यू, आप लोग का कोई डाउट वाला प्रॉब्लम वाला टॉपिक रहे तो लेट मी नो एंड ट्राई टू डू इट आउट. और इफ यू नीड टू डू सम प्रॉब्लम्स ऑन एनी सेक्शन प्रैक्टिस पार्ट ऑफ लेशन, लेट मी नो so that I can plan on the Sundays if it is possible for numerical solving on Sunday or something like that. आप लोग का जो भी टॉपिक बिल्कुल जीरो है या यू नीड ए प्रैक्टिस ऑन दैट टॉपिक, fastly I can revise the formulas and try to do the numericals based on the topic. ये तो रेगुलरली ऐसे चलते रहेगा. ये संडे तक I'm planning to complete this heat and thermodynamics. उसके बाद हम लोग असाइनमेंट सेशन करेंगे और इसके बाद उसके ऊपर के PYQs मैक्सिमम प्रैक्टिस करेंगे, बिकॉज इट हैज 5 क्वेश्चंस फॉर द कॉम्पिटिटिव एग्जामिनेशंस. तो 4 to 5 क्वेश्चंस अगर हम लोग थोड़ा परफेक्ट हो जाए ये वीक के अंदर, और नेक्स्ट वीक पूरा इस पे प्रैक्टिस करिएगा. एक वीक पूरा इस पे प्रैक्टिस करें, रोज 20-40 प्रॉब्लम्स करते रहें, तो देन यू विल गेट मास्टरी इन दिस टॉपिक. अभी तो मैं हल्लू डाल रहा हूँ, थोड़ा एक 4-5 दिन होने के बाद विल ट्राई टू इंक्रीज द स्पीड एंड एज वेल एज ऑफ योर एक्यूरेसी. ठीक है,
Yes, sir.
Yes, sir.
चलो ठीक है बेटा, बाय.